Welcome back to the podcast, everyone. Today, we're diving into a fascinating world, high-throughput materials research. It's a field that's revolutionizing how we discover and optimize new materials, and we're going to explore just how it's done.
That sounds exciting, Matthew. I always wondered how scientists deal with the sheer number of possible combinations when they work with alloys and other multi-component materials. It seems like an incredibly complex problem.
It absolutely is, Justin. Traditionally, materials scientists have faced a huge combinatorial challenge. Think about it, if you're working with an alloy that has even a few different components, the number of possible compositions explodes. Testing each one individually is incredibly time-consuming and expensive. This is what the paper by Kitchen and Gelman, High-Throughput Methods Using Composition and Structure Spread Libraries, addresses.
So, how do these high-throughput methods solve this problem?
They use clever strategies to create libraries of materials with continuous gradients in composition or surface structure. These gradients are often created as thin films with varying compositions across the sample. One of the most common is called a composition spread alloy film, or CSAF.
A CSAF? Could you explain what that is?
Sure. Imagine a thin film where the composition changes gradually across its surface. Instead of having many individual samples of different compositions, you have one sample that contains a whole range of compositions. This allows researchers to test a huge number of compositions simultaneously.
That's brilliant. How does that work in practice?
And what about characterization? How do you figure out the properties of each composition across the film?
That's where spatially resolved analytical techniques come in. These techniques allow researchers to probe the properties of the material at different locations across the CSAF, essentially measuring the properties as a function of composition. Think of techniques like energy dispersive X-ray spectroscopy or Raman spectroscopy. These can be combined to create high-resolution maps of the composition and properties across the entire film.
It seems like this would be incredibly helpful for studying corrosion or catalysis, where the composition plays a huge role in the material's behavior.
Absolutely, Joey. Kitchen and Gelman highlight several examples of this. In corrosion studies, for example, researchers can use a CSAF to identify the optimal composition of an alloy to maximize its resistance to oxidation. In catalysis, they can find the best alloy composition for maximizing catalytic activity. Similarly, surface structure spread single crystals, or S4CS, allow the study of the effect of surface structure on catalytic activity.
So, this approach reduces the need for numerous discrete experiments, leading to more efficient data collection and richer datasets, right?
Exactly, Gerind. This method dramatically accelerates the research process. A study that could have taken years to complete by traditional methods can be done much quicker. This allows researchers to explore far more compositions and conditions, leading to better models and a more complete understanding of material behavior.
That is remarkable. It sounds almost too good to be true.
Well, it's not without its challenges. One main challenge is analyzing the vast amounts of data these experiments generate. Powerful computational tools are needed to efficiently handle and interpret this data. But the potential advantages far outweigh the drawbacks.
It's fascinating to think about how this approach is impacting different fields like corrosion, catalysis, and electrocatalysis. It really seems like it's pushing the boundaries of what's possible in materials research.
Absolutely, Joey. These high-throughput methods are changing the game. The future of materials research strongly depends on them. As techniques continue to develop, we'll see even more efficient methods for creating and analyzing these materials libraries, leading to new discoveries and innovations at an unprecedented pace.
To summarize, the core idea behind this is that by using continuous compositional gradients instead of discrete samples, we significantly reduce the time and expense required to test numerous possible materials, allowing for quicker discovery of optimal compositions for various applications.
And that leads to a much deeper understanding of the complex relationships between composition, structure, and the resulting material properties.
Precisely. And that's what makes high-throughput methods so revolutionary in materials research. Thanks for joining us today, everyone. Join us next time for another fascinating discussion.